Hey everyone. In this last video, we're going to move on to quantifying uncertainty in our linear regression framework. And essentially, the the lessons that we learned in the previous videos regarding kind of the idea of the sampling distribution, how we compute standard errors and interpret standard errors as this, or essentially as the standard deviation in the sampling distribution across repeated data generating processes, how we compute confidence intervals, and how we think about hypothesis tests and the p-value. All these concepts and all these ideas can be directly kind of transported into the regression framework when we talk about uncertainty around our point estimates, around our regression coefficients, right? So let's jump right into it and just briefly review and refresh the linear regression model that we talked about in the past weeks. Okay, the model, the most basic bivariate model specification is, of course, our yi, our dependent variable. We have our intercept beta 1 as our slope coefficient, xi as the independent variable, and our error term epsilon I. Okay, and we have a couple of, or we have two important assumptions. One, the expectation of the error term being equal to 0. And we're going to talk more about that assumption in a second, and the variance of the error term being equal to sigma squared. So we have a constant variance across observations, and we're going to talk about that assumption in more detail in a second as well, right? So based on that kind of model for the data generating process, we can estimate the parameters beta 0 and beta 1 using least squares. So in order to estimate these or derive these least squares estimates, we minimize the sum of squared residuals, where the sum of squared residuals are just the sum of the squared errors between our y bar, between our yi, the observed outcome value, and our y hat, which is the predicted the predicted value of the linear model. Okay, so that's yi minus beta hat 0 minus beta hat 1 xi. These two components are y hat, and so the difference between yi and y hat, that's our observed error term. We take the square of that, sum that across all observations. That's the sum of squared residuals. And we take that term across the sum across all observations, and we minimize it with respect to beta 0 and beta 1 in order to get our least squares estimates. Okay, we went through that at length in previous videos, right? As I mentioned, there are two key assumptions in there about the underlying data generating process. The first key assumption is what is often referred to as the exogeneity assumption, which is that the mean of epsilon I, so the mean of the expectation of the error term, does not depend on xi. So it's in other words, the expectation of the error term conditional on xi is equal to the expectation of the error term, which is just equal to 0, right? So that's the exogeneity assumption. And then we have homoscedasticity, which basically just means that the variance of epsilon I does not depend on xi. So in other words, the variance of epsilon I conditional on xi is equal to just the variance of epsilon I. It's equal to a constant variance that we describe as sigma square. And those are two key assumptions in the regression framework that we will need in order to show, on the one hand, for the first one, to show that OLS is unbiased, and we did that in previous videos actually. And then the second one, homoscedasticity, we will need in order to derive simple standard errors for our regression coefficients. Okay, of course, there can be cases where these assumptions are violated, and we'll talk about these assumptions and violations of these assumptions much more in 702 when we talk about OLS in much more detail. But just briefly, exogeneity, one big violation of the exogeneity assumption is if we have omitted variable bias. If there are variables that are basically part of the data generating process that are correlated with X and correlated with Y, but they're not included in our OLS specification, what that results in is that the error term is then correlated with our X's, which means that this assumption that the expectation of the error term conditional on X is not equal to 0, or the expectation of the error term irrespective or marginalized over X, and then we violate the exogeneity assumption, right? So omitted variable bias is just one example of basically violating the exogeneity assumption. The homoscedasticity assumption is a little bit more tricky, but we can still think about examples where the error variance is larger or smaller for different subgroups of the population, for example, right? So, for example, you could think of cases where specific groups, for example, if you look at gender differences, where the error term for men is larger or smaller compared to women, and that's a case where we have where the homoscedasticity assumption is violated. Or you could think of if you look at the effect of income on some dependent variable, you could think of a case where income doesn't only increase the average value of the that income variable, but also increases the variance of that income variable, and that again would imply that the homoscedasticity assumption is likely to be violated, right? So there are cases where each of those assumptions can be violated. The key point to keep in mind is, though, that there is an easy fix for heteroscedasticity, and this is where we get into robust standard errors, and we'll talk more about them next semester, not this semester, but not for endogeneity, right? Endogeneity induces bias in our estimates, and we have to fix, for example, omitted variable bias. We have to fix by including those variables in our model. With heteroscedasticity, at least in large samples, there are easier fixes. Okay, and we'll talk about more about these assumptions and their violations in the upcoming semester. Okay, under these assumptions, homoscedasticity and exogeneity, we can derive a couple of useful statistical properties of least squares. And again, we already covered in previous weeks the deriving unbiasedness of the OLS estimator under certain assumptions. But we can also kind of quantify the uncertainty around our beta hats. And again, in order to kind of characterize the uncertainty around our point estimates or around our beta hats, we rely on the same idea of a hypothetical repeated data generating process. Repeated sampling and looking at, you can think of computing one slope parameter for our sample, just like we had an X bar for our single sample, and we want to characterize the uncertainty around that regression coefficient, around that slope parameter, by examining how much that parameter would vary across repeated sampling procedures, right? So how would this repeated sampling procedure essentially look like? You could think of this as either sampling yi and xi according to the underlying model that we specified, or equivalently, you could think of sampling xi and epsilon I from the population, and then computing yi based on xi and epsilon I, you're basically according to the model. But essentially that would each imply basically kind of repeating the data generating process and then running a regression and obtaining our beta hat 0 and our beta 1, beta 1 0, sorry, beta 0 hat and beta 1 hat for one specific data generating process for one specific sample. But we could again repeat that process and then again kind of think about a sampling distribution of our regression coefficients across repeated data generating processes, right? As I mentioned, we already showed in previous week that under exogeneity, beta 0 and beta 1 are unbiased, right? They are in expectation equal to the true population beta 0 and the true population beta 1, right? Under exogeneity and homoscedasticity, the standard errors are unbiased as well. And we can essentially use the same logic from the central limit theorem to characterize the uncertainty around our estimates over repeated sampling procedures, right? So similar to kind of the examples that we went through with our X bar with population proportions, we can compute, for example, 95% confidence intervals around our intercept and around our slope coefficients by subtracting and adding the standard error times our critical value here for a given significance level, here the 95% level, in order to provide an interval. And again, the logic of that 95% interval is that assuming basically assuming or over repeated sampling procedures, the 95% confidence interval will contain over repeated samples, this interval will contain the true population value, the true beta 0 or the true beta 1, 95% of the time. Again, exactly the same logic applies with population averages that we talked about. Just here, instead of computing a population average, the statistic that we're computing, or the point estimate that we're looking at, is a regression coefficient, either an intercept or a slope coefficient. Okay, so that means we can also directly conduct hypothesis tests. For example, looking at a hypothesis test of beta 1 hat being equal to some beta 1 star, or being equal to 0, for example. And then again, an alternative hypothesis of beta 1 hat not being equal to that null hypothesis. Okay, we can again, invoking the central limit theorem, compute test statistics just using exactly the same logic that we used before. Here, looking at the difference between our beta 1 hat minus our assumed beta 1 star, given our null hypothesis, divided by the standard error of beta 1 hat, which is which is again the variance of beta 1 divided by, or kind of similar to the previous case where we had the variance of X bar divided by the sample size. So we compute the standard error of beta 1 hat, we look at the difference between beta 1 hat and beta 1 star, and that kind of normalized that normalized test statistic then follows a standard normal distribution with mean 0 and standard deviation 1, because it is normalized by the standard error of beta 1 hat. Okay, so even though we often rely on the central limit theorem and so therefore this test statistic is usually normally distributed, oftentimes what we actually use is the t-distribution. So we're kind of similar to the previous discussions where we said, assuming the central limit theorem, we know that this is normally distributed for large enough sample sizes, so we can directly kind of look at the normal distribution to compute our p-values. We can kind of use the t-distribution. The t-distribution usually requires that the underlying variables or the underlying parameters are normally distributed. um, which is not necessarily the case. But keep in mind that for large sample sizes, the t-distribution approaches the normal distribution. So again, this is kind of a conservative uh, um, a conservative standard to just use the t-distribution, even if we rely on the central limit theorem, because with a large enough sample size, the t-distribution approaches the normal distribution anyhow, and for smaller sample sizes, it essentially represents a more conservative test. Okay, so again, I went through this fairly quickly, but the key point is that all the pieces are essentially follow the same arguments that we discussed previously when we talked about sample proportions or X bar or proportion test and so on, right? The way we compute this confidence interval, or the way we think about hypothesis tests and p-values and test statistics with these parameters, is exactly the same way we talked about hypothesis tests about population means being equal to certain critical to certain values, okay, like 0.5 for proportions, okay. So the same logic applies. So let's go back to one of our initial examples that we used to introduce the regression framework, and now kind of go through the same procedure, but now taking into account the uncertainty around our estimates and kind of thinking about what exactly this uncertainty means. And the specific example that we're going to look at in particular is the study on facial appearance and politics, right? And so this was an experiment, remember, where respondents were given the picture of two unknown politicians who ran for office, or candidates who were running for office. And all these, the respondents, the participants in the experiments, all they had to do was to evaluate which of these pictures or which of these people seemed more competent, right? This is one example of the study. You have two people who might be familiar to you or might not be familiar to you. Turns out they both ran in the 2004 was sorry. They both ran in the 2004 Wisconsin Senate race. It's Russ Feingold, Democrat, who actually received 55% of the vote, and Tim Michaelis, Republican, received 44% of the vote. The key point here is that participants were just asked to rate the competence, and what the researchers then looked at was the relationship between the competence rating among participants who didn't know those candidates and their actually performance, or their actual vote margin in elections, right? So there were a bunch of different candidates. Their competence ratings were measured across participants, and then we looked at to what extent the competence rating is related to their actual vote margin of victory. Okay. So we've already looked at these data sets, but just to reiterate, to go through this, we have our this was the face.csv data set that contained data from this experiment. We compute the Democratic vote share and the Republican vote share for those candidates, and then compute the margin as the difference between the Democratic vote share and the Republican vote share, and we can plot we can just look at a basic scatter plot of the relationship between the competence rating, the relative competence rating for the Democratic candidate and the Democrat, or the difference in the vote shares. So where positive values indicate higher vote share for the Democratic candidate, and negative ratings indicate or smaller values indicate higher values for the Republican or higher vote share for the Republican candidate. Okay, and in addition to the basic scatter plot, we include a linear regression model where the dependent variable is, of course, the vote share, or the relative vote share, and the independent variable is the competence rating for the Democratic candidate. And we're adding this regression line to our plot. And this is a plot that you've seen before in previous weeks when we introduced this idea of the linear regression framework in the bivariate case, right? So we see we have a positive relationship. An increase in competence scores is associated with an average increase in the Democratic margin in the vote share. Okay. But the question is, how much uncertainty is there around our estimates, and to what extent would we reject the null hypothesis that there is no relationship between the competence ratings and the Democratic vote win margin, essentially. Okay. So in order to interpret these regression results, one way to directly get the full information based on that regression results, including hypothesis tests for individual coefficients, as well as standard errors for those coefficients. The quick way to basically get the summary for that regression model is to use the summary command, which we looked at briefly to examine the R squared, but we didn't really look at the additional output that was part of that summary command, because up until this point we didn't really talk about uncertainty and standard errors and this idea of the sampling distribution. Okay, but now if you look at the summary of that regression model, that fit, we see we have our point estimates. We have an intercept of minus 0.31, which of course is doesn't really have a clear substantive interpretation, because well, the competence rating for Democrats, or this is kind of almost an extrapolation because the competence rating was almost never just equal to 0. But given this result, if the competence rating for the Democratic candidate was equal to 0, then the expected vote margin of the Democratic candidate versus the Republican candidate is around 0.31, so 31 percentage points in favor of the Republican candidate. Okay. More interesting, of course, is the slope coefficient for the effect of the competence rating of the Democratic candidate, and we have an estimate of 0.66, which implies that a 1 unit increase in the competence score, which is basically an increase from minimum to maximum, because it was basically bound between 0 and 1, leads to an increase in the estimated vote margin of 0.66. So that's a 66 percentage point increase if we go from like the theoretical minimum of the competence rating to the theoretical maximum of the competence rating. So that in of itself is a huge huge effect on the vote margin. Okay. But now, in addition to kind of interpreting this point estimate, we can now also examine the uncertainty around those estimates by looking at first the standard error. And of course, the standard error describes basically the average deviation kind of over repeated samples in our sampling distribution, how much this point estimate would deviate across repeated data generating processes, right? And based on that standard error, we can basically under the null hypothesis that this point estimate is actually equal to 0 in the population, we can compute a t-value. So that's basically assuming that this, going back to the test statistic, assuming that the reference distribution is a t distribution centered at 0, we can compute the t statistic and the related p-value, which again is the p-value under the null hypothesis that the coefficient is equal to 0. Okay, so essentially what we see here is the p-value for that specific parameter under the null hypothesis that this parameter is actually equal to 0, right? And so we see that the p-value both for the intercept and for our slope parameter is extremely slow. So that's 6 times 10 to the power of minus 6, and this is 8 times 10 to the power of minus 7. So much smaller than 0.001. And so that's why we have 3 stars here, because the significance level is smaller than 0.001. So in other words, under the null hypothesis that the true in the population this parameter was equal to 0, it is extremely unlikely that in our individual sample we would observe a slope coefficient of 0.66 given our sample size, right? The probability is smaller than 0.001. In other words, we would reject the null hypothesis that that slope coefficient is equal to 0 at the 0.001 significance level. Okay, so this is the information that is directly provided by the summary command. Again, always testing against the null hypothesis that each of these parameters is equal to 0 in the population. Okay. So as we talked about at length in previous videos, the interpretation of beta 1 of our slope parameter is the average increase in yi that is associated with a 1 unit increase in xi, right? And in this case, a 1 unit increase in our competence rating was, of course, basically going from the absolute theoretical minimum in competence rating to the absolute maximum in competence rating, and both 0 and 1 were actually never observed in the sample, right? So this, you always have to keep in mind what a 1 unit increase in our xi actually implies. Okay. In many cases, it's a little bit difficult to interpret just beta 1 or some slope parameter just on its face, and so what we often want to do is we want to compute expected values or predicted values for specific scenarios, and we kind of had examples like that previously, especially in the context of interpreting regression coefficients, where we wanted to compute predicted values for specific scenarios, right? But now what we want to keep in mind is that when we compute these predicted values or expected values, we have to also incorporate the kind of estimation uncertainty around our estimates and kind of be sure to communicate our uncertainty around our predictions as well. In general, one key distinction that we have to make is between expected values of our based on our model, which is the average outcome in yi, given that xi is equal to some scenario value x. Okay, so that's the expected value, basically assuming the point estimates of our model, and then we have the predicted value, which is the prediction of the outcome given that xi is equal to x, right? And so at a first look, these seem to be kind of equivalent, right? These seem to be exactly the same, but they're not when we talk about introducing the uncertainty around our prediction, right? Keep in mind here we have the average outcome given xi equal to x, right? So that's the average across, again, repeated, you could think of this as repeated sampling procedures. What is the average outcome given that xi is equal to x? And this is for one specific sample, so to speak, what is the predicted outcome for xi being equal to x, right? And that's the key distinction that we have to keep in mind, right? Of course, our point estimate for our prediction is just, in this case, in a bivariate case, beta 0 plus beta 1 x. And we can ultimately compute two different standard errors. One, the standard error for the expected value, which is just basically the standard, or the variance of the sum of beta 0 and beta 1x, which is, of course, the sum of the variances plus the covariance, or 2 times x times the covariance of beta 0 and beta 1, which is just, using the basic rules about the variance of a sum of random variables that are not uncorrelated. Beta 0 and beta 1 are not uncorrelated. And so we have beta 0 plus 2 times the covariance of beta 0 and beta 1, where we can pull x in front of the covariance, and x squared times the variance of beta 1. Again, pulling x squared in front of the variance, or pulling x in front of the variance, which turns into x squared. Okay, so that's the standard error for the expected value. How does the standard error for the predicted value now change? And the key here is that rather than looking at the average outcome and just looking at kind of the estimation uncertainty, or taking into account the estimation uncertainty, in this case we also take into account the variance of our epsilon. So in this case, when we're talking about the standard error for the predicted value, you were taking into account the fact that we have basically an error term where for each individual prediction we have a deviation, basically a random or a fundamental uncertainty around our outcome that we have to take into account, right? We don't have to take this variance of the error term into account when we talk about the expected value, because we can think of because the variance of the error term, of course, or the error term itself, the expectation of the error term is equal to 0. So if we take an average of a lot of kind of repeated data generating processes, that error term is equal to 0. So that just cancels out when we look at the average outcome given xi being equal to x. When you look at an individual prediction for one specific realization, we have to take into account that error term, and we have to take into account that variance in order to compute the standard error for the predicted value. Okay. But no matter whether we're talking about the standard error for the expected value or the standard error for the predicted value, we can construct the confidence intervals and conduct hypothesis testing in the same manner as we discussed before. Okay. All right. So now let's jump briefly into how we can do this actually in R. How we can compute expected and predicted values in R. And again, this is kind of going back to an example that we talked about before. Specifically, we already talked about using the predict function, where we take our model fit that we already estimated, and we provide a new data frame for a specific scenario of our independent variable, and we want to compute predicted values for that specific scenario. And so here, for example, we want to compute predicted values for competence ratings of 0.1, 0.5, and 0.9. And the predicted values that we get are minus 0.246, 0.0179, and 0.282. So those are the predicted vote margins for positive values in favor of the Democratic candidate, negative values, of course, in favor of the Republican candidate. Okay. But of course, these by themselves don't take into account the uncertainty around these estimates. If we want to kind of get the standard errors for those predictions, we can include the argument se.fit equals to true, and we get the standard errors, and that's just taking into account these standard errors basically only take into account the estimation uncertainty. But we also have the residual scale, which basically takes into account this variance of the error term. Okay, and so based on this standard error and this residual scale, we could then compute the standard error for our expected value and for the predicted value around that point estimate. Okay. Luckily, we don't have to do that manually. We can directly do this using the predict function. And the way we do this is we can basically just say tell R or include an additional argument in the predict function where we tell R that we want to include an interval, either a confidence interval. That confidence interval tells R that we want to examine the uncertainty around the expected value, which is now the lower and upper basically the lower bound and the upper bound of the, in our case here, the 90% confidence interval over repeated sampling procedures, how much the expected value for x being equal to 0.1, 0.5, and 0.9 is across basically across repeated sampling procedures. Okay. On the other hand, if we want to look at the prediction uncertainty, so if we want to take into account not only the, if we don't only want to look at the uncertainty around the expected value for a specific scenario of our independent variable, but rather want to take into account the fundamental uncertainty, so want to take into account the error term in our model, we can, rather than saying the confidence or rather than asking for the confidence interval, we can ask for the prediction interval, which again now takes into account not only the estimation uncertainty around our estimates, but rather takes into account this error term as well. And you could think of this as the additional uncertainty for individual predictions rather than the uncertainty around the average outcome conditional on x taking a specific value. And we see, of course, that the lower and upper bounds, the limits of that prediction interval is much larger than the lower and upper bound of the confidence interval. And again, here we're talking about the uncertainty around the expected value over repeated samples in our prediction. Or sorry, so basically we're talking about the 95% or the 90% confidence interval for the expected value conditional on x taking specific values. And here we're looking at the 90% prediction interval, not directly over or in addition to this estimation uncertainty, taking into account the fundamental uncertainty. So taking into account this the prediction error, this epsilon, the variance of the error term in our individual predictions. Okay. And now going back to our previous example where we predicted our regression results, we can now, in addition to the linear fit that we plotted previously, we can compute our predictions based on our linear fit, including the confidence intervals for our predictions from 0.1 to 0.9. And if we do that and add this to our scatter plot that we looked at previously, we now not only have our linear fit for this bivariate relationship between competence scores and the democratic vote margin, but in addition we have a lower and upper bound for the confidence interval, for the 95% confidence interval around the expected value conditional on the competence score ranging from 0.1 to 0.9, right? And so here again, this is the uncertainty um, around the expected value conditional on x over repeated samples. So this is again this logic of the confidence interval. If we alternatively looked at the prediction interval, this would not be the uncertainty around the expected value over repeated samples, but rather the uncertainty across the predictions, taking into account the error term for that individual sample. Okay, so the lower and upper bound would be much larger here, of course. Okay. All right. So now, after kind of walking through regression and taking into account uncertainty in this regression framework, I just want to mention a few key points regarding statistical inference with multiple regression. And of course, the first thing we have to keep in mind is that correlation does not imply causation, right? So in the regression framework here, we had just a bivariate regression with one independent variable and one dependent variable. And of course, as soon as we have omitted variables, we could potentially essentially have kind of a spurious relationship, right? As I mentioned, as soon as we have omitted variables, we violate the exogeneity assumption and we have a bias in our estimates, okay? We can, of course, to some extent, fix this by adjusting for multiple confounding variables, and this is what we talked about in previous weeks, where we talked about including control variables in our models, so x2 up to xp, including our models, conditioning on our models in order to get rid of this omitted variable bias, but we still have to take into account that even if we control for a relevant set of variables, we cannot necessarily assume that the effects that we observe can be interpreted as causal effects. So the interpretation of an individual beta j slope coefficient is still just one of association and not one of causation. So an increase in the outcome beta or the coefficient beta j is still interpreted as an increase in the outcome associated with a 1 unit increase in xij when the other variables basically stay constant at their respective value. The key point here is that this is still a statement about an association, a statistical association that is not necessarily causal. Okay. We can, again, in this multiple regression framework, we can still compute confidence intervals for beta j hat. We can compute expected values, predicted values, just in the same manner that we talked about before. We can also engage in hypothesis tests for beta j, for expected values and predicted values in the same manner that I discussed. Okay. Now, the last question that you might be wondering is, well, even if we control for potential relevant omitted variables, and we can still not interpret these associations as causal, how can we actually move from correlation to causation, right? And ultimately, well, first of all, what does it mean ultimately to have a causal interpretation? And we talked about this in the context of the potential outcomes framework. Ultimately, the causal interpretation of the linear regression in the linear regression framework means that a 1 unit increase in some xi actually causes a change in yi by beta, holding the other variables constant, right? And so essentially, we can only make this causal interpretation that the change in x1, xi actually caused a change in y if essentially if xi is randomized. If we have a true, a true randomized treatment assignment, for example, then we can make this causal interpretation. As soon as we don't have a randomized truly randomized assignment for x1 xi, then we can't directly make this causal interpretation. Okay. Of course, randomized experiments are difficult to do. Often, in many cases, for example, when we talk about research in international relations or comparative politics, they're ultimately not, we cannot directly randomize countries into specific conditions, right? So what are the alternatives? And we talked about some of these alternatives in past weeks, and I just want to reiterate them and kind of bring them back to your memory to kind of keep them in mind in the context of the regression framework that we talked about. One way to kind of try to get closer to this causal interpretation is to find natural experiments where the treatments are basically are not assigned completely randomly, or you don't have, while you don't have control over the treatment assignment, the treatments are assigned haphazardly, or at least basically independent of other potential confounding factors, right? We talked about this example of the Vietnam draft lottery. You can talk about, or another example of like natural experiments is using birthdays or weather conditions as like exogenously caused events. Or one of the assignments, or not an assignment as part of the problem sets, but one of the exercises in the book focuses on the assassination of political leaders as like an exogenous natural experiment, essentially, right? So those are examples of natural experiments where the treatment are assigned in a way that is essentially exogenous to potential confounding factors. And then we can get closer to this causal interpretation of our regression coefficients. Another context that we talked about is this idea of difference in difference, or before and after designs, for example, in the context of the increasing minimum wage study that we talked about at length. And the last point that is emphasized or discussed more in the book that you definitely should check out in more detail is this idea of regression discontinuity designs, where we take advantage of arbitrary cutoff points that naturally occur in the world. One example is, for example, test scores as a deciding factor whether or not you get into a program or not, and then looking at test scores that are just above the threshold and just below the threshold to examine the effect of being part of a specific program. But there are other examples. I mentioned admissions, financial aid, welfare eligibility, and so on, are all examples of arbitrary cutoffs based on some selection variable that you can use in the context of regression discontinuity designs. All those are essentially kind of ways and strategies and identification strategies to get you closer to interpreting the regression coefficients in terms of the causal effect of X on Y, right? But the key point is that just controlling for additional variables is not enough. It doesn't get you to this causal interpretation. Even if you are sure that you don't have omitted variable bias, you can't move from correlation to causation without invoking additional assumptions or invoking or using strategies like natural experiments or regression discontinuity designs, and so on. All right. This video ended up a little bit longer than I wanted it to be, but we're done for this week. I'm looking forward to your questions in our Q&A session.